Hello there, and welcome to another gentle journey with the Sleepy Astronaut, where the wonders of the cosmos meet the comfort of your bedside. Tonight we're drifting northward, far beyond the city lights and into the realm of one of nature's most breathtaking spectacles. We're exploring the ethereal dance of the northern lights, those mysterious curtains of colour that have captivated humanity for millennia, and continue to paint the polar skies with their otherworldly glow. I'm curious, where in the world are you joining me from tonight? Are you perhaps somewhere where the aurora borealis graces your winter skies? Or are you like so many of us, dreaming of that magical moment when you might witness this celestial ballet for yourself? There's something rather fitting about discussing the northern lights in the quiet hours, when the world feels hushed and the sky seems vast and full of possibility. If you find these cosmic wanderings soothing, if they help you unwind after a long day, or simply satisfy that gentle curiosity about the universe we call home, I'd be ever so grateful if you'd give this video a like and perhaps consider subscribing. It helps this little corner of wonder reach others who might need a peaceful pause in their evening too. Now, I do hope tonight's exploration isn't so fascinating that it keeps you awake, but if it does, well, at least you'll drift off, knowing a bit more about one of the most magical phenomena our planet has to offer. So settle in, let your thoughts slow, and let's begin this quiet adventure together. Because somewhere in the dance between solar winds and magnetic fields, between ancient myths and modern science, lies the story of the aurora borealis. And it's more extraordinary than you might imagine. The northern lights have been whispering their secrets to humanity for thousands of years, long before we understood the science behind their shimmering curtains. To witness them is to see the invisible forces of space made visible, a reminder that our planet is not floating alone in the cosmic dark, but is constantly bathed in the energy of our nearest star. Picture, if you will, a moment roughly 4.5 billion years ago. The Sun, that magnificent furnace at the centre of our solar system, began its long career of nuclear fusion, converting hydrogen into helium and releasing tremendous amounts of energy in the process. But the Sun doesn't just give us light and warmth, it also sends out a constant stream of charged particles, a phenomenon we call the solar wind. These particles, mostly protons and electrons, race through space at speeds of up to 900 kilometers per second, creating an invisible river of energy that flows past every planet in our solar system. Now you might wonder, if these particles are constantly streaming toward Earth, why aren't we bombarded by them every moment of every day? The answer lies in one of our planet's most elegant protective systems, something so fundamental to life as we know it that we rarely stop to marvel at its quiet, constant work. Earth possesses a magnetic field generated deep within its molten core that acts like an invisible shield surrounding our entire planet. This magnetic field, called the magnetosphere, extends far into space, creating a protective bubble that deflects most of the solar wind around us, much like water flowing around a stone in a stream. But here's where the story becomes truly beautiful. The magnetosphere isn't perfectly spherical. It's compressed on the side facing the Sun and stretched into a long tail on the side facing away, creating a teardrop shape that extends far beyond the Moon's orbit. At the poles, something remarkable happens. The magnetic field lines converge, creating pathways where some of those charged particles from the solar wind can slip through our magnetic defences and enter our atmosphere. It's at these polar regions, roughly 60 to 70 degrees north and south latitude, where the magic begins to unfold. When these high-energy particles from space collide with the gases in our atmosphere, they create what scientists call excitation. The particles transfer their energy to the atoms and molecules of our atmosphere, particularly oxygen and nitrogen, causing them to emit light. It's rather like striking a bell and hearing it ring, except in this case the bell is an atom, and instead of sound it produces a photon of light. Different gases produce different colours, creating the aurora's characteristic palette. Oxygen, when excited at high altitudes around 300 kilometers above the surface, glows red. At lower altitudes, around 100 to 200 kilometers, the same oxygen produces that familiar green glow that many consider the signature color of the Northern Lights. Nitrogen contributes blues and purples, while other trace gases add subtle hints of yellow and pink to the atmospheric canvas. But the aurora is far more than just a pretty light show. It's a visible manifestation of the complex relationship between our planet and the sun, a reminder that space weather affects us just as terrestrial weather does. When the sun is particularly active, releasing bursts of energy in events called solar flares or coronal mass ejections, the aurora can become more intense and visible at latitudes much farther south than usual. The indigenous peoples of the Arctic have known and revered the Northern Lights for countless generations. The Inuit have various names for the phenomenon, including Aksanit, which refers to the souls of the departed playing games in the sky. Finnish folklore speaks of the Revontule, or firefox fires created by a magical Arctic fox running so fast across the snow that its tail swept up flakes into the sky, where they caught fire and created the dancing lights. The Sami people of northern Scandinavia believed the aurora was the energies of the departed, and many cultures saw the lights as omens, sometimes good, sometimes foreboding. The Vikings thought the aurora was the reflection of light off the shields and armour of the Valkyries as they led fallen warriors to Valhalla. There's something deeply moving about these ancient interpretations, the way our ancestors looked up at the same lights we see today and wove stories to explain their beauty and mystery. It wasn't until the 17th century that scientists began to study the aurora systematically. The great astronomer Galileo Galilei is credited with coining the term aurora borealis in 1619, combining Aurora, the Roman goddess of dawn, with Boreas, the Greek god of the north wind. Even then, the true nature of the lights remained elusive for centuries. The breakthrough came in the early 20th century, when Norwegian physicist Christian Birkeland proposed that the aurora was caused by charged particles from the sun interacting with Earth's magnetic field. His theory was initially met with skepticism, but as our understanding of plasma physics and space weather grew, Birkeland's insights proved remarkably prescient. Today we know that the aurora is part of a much larger system of space weather that affects everything from satellite communications to power grids. During particularly intense geomagnetic storms, the aurora can be visible as far south as the northern United States, and the same charged particles that create the beautiful lights can also disrupt radio communications, interfere with GPS systems, and even cause power outages. But let's return to the wonder of it all. The northern lights aren't just random flashes of colour. They form distinct patterns and shapes that have their own names and characteristics. There are arcs, the most common form, which appear as gentle curved bands of light stretching across the sky. Rays shoot upward like searchlights, while bands undulate and dance like cosmic ribbons in a celestial breeze. One of the most spectacular forms is the corona, which appears when you're directly beneath an active aurora. The lights seem to radiate from a central point directly overhead, creating the illusion of a vast crown of light. It's a perspective that few are privileged to witness, but those who have described it as one of the most moving experiences of their lives. The aurora also has a rhythm, a pulsing quality that can be slow and stately or quick and energetic. Sometimes the lights appear to flicker like candle flames. Other times they sweep across the sky in waves. Scientists have discovered that these variations correspond to different types of particle interactions and magnetic field fluctuations, but the technical explanation somehow doesn't diminish the sense of witnessing something truly magical. What makes the Northern Lights even more fascinating is their unpredictability. Unlike a sunset, which you can count on happening at a specific time each day, the aurora is a wild phenomenon that appears when conditions are just right. The solar wind must be strong enough, the magnetic field orientation must be favourable, and the sky must be dark and clear enough to see the lights. It's this combination of factors that makes aurora watching both thrilling and challenging. For those who chase the northern lights, patience becomes a virtue. Aurora photographers and enthusiasts often spend hours in the cold, dark wilderness waiting for the lights to appear. Sometimes they're rewarded with spectacular displays that dance for hours. Other times they see only a faint green glow on the horizon or nothing at all. But it's precisely this uncertainty that makes each sighting so precious. The best places to see the northern lights lie within what scientists call the auroral oval, a ring-shaped zone around the magnetic North Pole. This includes northern Alaska, northern Canada, Greenland, northern Scandinavia, and northern Russia. But the oval isn't fixed. It expands and contracts based on solar activity, sometimes bringing the aurora to places where it's rarely seen. Cities like Tromsø in Norway, Fairbanks in Alaska, and Yellowknife in Canada have become pilgrimage sites for aurora enthusiasts. These communities have built entire industries around aurora tourism, offering everything from heated glass igloos to specialized photography tours. There's something rather wonderful about places where the rhythm of life is partially dictated by the cosmic dance overhead. The best time to see the northern lights is during the long, dark nights of winter, particularly around the equinoxes in March and September, when geomagnetic activity tends to be highest. But the aurora doesn't keep to human schedules. It can appear at any time during the dark season, and its intensity can vary from a subtle glow that's barely visible to the naked eye to brilliant displays that illuminate the entire landscape. Modern technology has revolutionized our ability to predict and study the aurora. Satellites monitor solar activity and can give us advance warning of geomagnetic storms that might produce spectacular displays. Ground-based magnetometers and all-sky cameras provide real-time data on auroral activity. Smartphone apps can now alert aurora watchers when conditions are favourable, though there's still no substitute for simply looking up at the sky on a clear, dark night. The aurora also has its southern counterpart, the aurora australis, or southern lights, which occurs around the Antarctic region. The southern lights are essentially the same phenomenon as the northern lights, created by the same solar particles interacting with Earth's magnetic field, but they're much less accessible to most people due to the remote location of the Antarctic continent. Interestingly, the northern and southern auroras are often mirror images of each other, occurring simultaneously as the same stream of solar particles interacts with both poles of Earth's magnetic field. This conjugate relationship was one of the key pieces of evidence that helped scientists understand the true nature of the aurora. For scientists, the aurora serves as a natural laboratory for studying plasma physics and space weather. The same processes that create the beautiful lights also occur throughout the universe, from the magnetospheres of other planets to the far reaches of interstellar space. By studying the aurora, we gain insights into fundamental physical processes that govern much of the visible universe. Space agencies around the world have sent missions to study the aurora from above, providing us with breathtaking images and data that would have been impossible to obtain from the ground. The European Space Agency's cluster mission, NASA's Themis satellites and other spacecraft have revealed the three-dimensional structure of auroral displays, showing us that what we see from Earth is just a small part of a much larger phenomenon extending far into space. These orbital observations have revealed that the aurora isn't just a thin curtain of light, but rather a complex, three-dimensional structure that can extend hundreds of kilometers into space. The particles that create the aurora follow the invisible highways of Earth's magnetic field lines, spiraling downward in helical patterns that create the characteristic vertical structure of auroral rays and columns. But perhaps what's most remarkable about our modern understanding of the aurora is how it connects the very small to the very large. The same quantum mechanical processes that govern how individual atoms emit light also shape the grand displays that can span entire continents. When a single electron from the solar wind collides with an oxygen atom in our atmosphere, it sets in motion a chain of events that can produce a photon of green light that travels 100 kilometers to reach your eye. Multiply that interaction by trillions, and you have an aurora. The aurora also teaches us about the delicate balance that makes life on Earth possible. Without our magnetic field, the solar wind would gradually strip away our atmosphere, much as it appears to have done to Mars billions of years ago. The same magnetic field that protects us from harmful radiation also creates the conditions necessary for the aurora to exist. In a sense, the Northern Lights are a visible celebration of the invisible forces that keep our planet habitable. Climate change is beginning to affect the aurora in subtle but measurable ways. As greenhouse gases warm the lower atmosphere, the upper atmosphere where the aurora occurs is actually cooling. This cooling causes the atmosphere to contract slightly, which can affect the altitude at which auroral emissions occur. It's a reminder that even phenomena that seem completely removed from human activity are connected to the complex systems that govern our planet's climate. The aurora has also played an unexpected role in the development of radio technology. In the early days of radio communication, operators noticed that their signals would sometimes be disrupted during periods of intense auroral activity. This led to some of the first systematic studies of the relationship between solar activity and terrestrial phenomena. Today, amateur radio operators still monitor auroral activity because the same charged particles that create the lights can enhance radio propagation under certain conditions. For photographers, the aurora presents both incredible opportunities and unique challenges. The lights are constantly moving and changing, making them difficult to capture with traditional photography techniques. Modern digital cameras have made aurora photography more accessible, but it still requires patience, skill, and often a willingness to stand in sub-zero temperatures for hours at a time. The reward, however, is the chance to capture images of one of nature's most spectacular displays. The colours of the aurora that we see depend not only on the gases in our atmosphere, but also on the sensitivity of our eyes. Human vision is most sensitive to green light, which is why the green glow of oxygen is often the most prominent colour we observe. But cameras can capture wavelengths of light that our eyes cannot see, revealing reds, purples, and blues that may be present but invisible to the naked eye during the display. Time-lapse photography has revealed the aurora's true dynamic nature. What might appear to be a static arch of light is actually in constant motion, with waves of brightness rippling along its length like wind through a field of grain. Some auroras pulse with a rhythm that seems almost musical, while others dance with an energy that appears almost alive. These movements reflect the complex interplay of magnetic fields and charged particles high above our heads. The aurora has inspired countless works of art, literature, and music. Composers have written symphonies attempting to capture the ethereal quality of the lights, while painters have struggled to recreate their otherworldly colours on canvas. Writers have used the aurora as a metaphor for everything from divine inspiration to the boundary between the known and unknown. There's something about the aurora that seems to touch a deep part of the human spirit, perhaps because it represents a visible connection to the cosmos that surrounds us. Indigenous astronomers and skywatchers developed sophisticated methods for predicting auroral activity long before modern science provided explanations for the phenomenon. They observed correlations between solar activity, weather patterns, and the behaviour of the lights, developing oral traditions that passed this knowledge from generation to generation. Modern scientists are increasingly recognizing the value of this traditional knowledge and working to preserve and study these ancient observational techniques. The aurora also serves as a reminder of our planet's place in the solar system. Earth is just one of several planets that experience auroral displays. Jupiter's auroras are powered by its volcanic moon, Io, which spews charged particles into the giant planet's magnetosphere. Saturn's auroras are influenced by its complex ring system and many moons. Even Mars, despite its weak magnetic field, experiences localized auroral displays in regions where ancient magnetic fields are still embedded in the planet's crust. These planetary auroras help us understand the diversity of magnetic environments throughout the solar system and provide clues about the conditions that might exist around planets orbiting other stars. As we discover more exoplanets, particularly those in the habitable zones of their stars, the study of auroral phenomena becomes increasingly relevant to our understanding of where life might exist elsewhere in the universe. The technology developed to study Earth's aurora has applications far beyond atmospheric science. The same instruments used to measure auroral particles and magnetic fields are used in fusion energy research, where scientists are trying to harness the same processes that power the sun. The plasma physics principles that govern auroral displays are fundamental to understanding everything from solar flares to the behavior of matter in the extreme environments around black holes. For many people, seeing the northern lights represents a profound spiritual experience. There's something about witnessing this cosmic dance that puts our daily concerns into perspective and reminds us of our connection to the larger universe. The aurora doesn't care about our schedules, our deadlines, or our worries. It simply exists, following the ancient rhythms of solar activity and magnetic fields that have persisted for billions of years. The silence that often accompanies auroral displays adds to their otherworldly quality. Unlike thunderstorms or other dramatic natural phenomena, the aurora is completely silent. The only sounds are those of the environment around you, the crunch of snow underfoot, the distant call of an Arctic owl, or the gentle whisper of wind through the trees. This silence somehow makes the visual spectacle even more profound, as if you're witnessing a secret conversation between Earth and space. Some aurora watchers report hearing sounds during particularly intense displays, describing crackling or whooshing noises that seem to correspond to the movement of the lights. While scientists remain divided on whether these sounds are real or psychological, recent research has suggested that under certain conditions, the aurora might indeed produce very faint sounds through electrostatic discharge in the atmosphere near the observer. The aurora also has a seasonal rhythm that reflects the complex relationship between Earth's magnetic field and the solar wind. The equinoxes, when day and night are equal length worldwide, tend to produce the most intense auroral activity. This happens because the orientation of Earth's magnetic field relative to the solar wind changes throughout the year, and the equinoxes represent times when the geometry is most favourable for solar particles to enter our magnetosphere. But the aurora is also unpredictable in ways that continue to challenge our understanding. Sometimes, during periods of low solar activity, brilliant displays appear unexpectedly. Other times, when all the conditions seem perfect for a spectacular show, the aurora fails to materialize. This unpredictability is part of what makes aurora watching so compelling. You never know when you might witness something truly extraordinary. The aurora has also become a symbol of climate change awareness. As our planet warms, the Arctic regions where the aurora is most visible are experiencing some of the most dramatic changes. The communities that have lived with and celebrated the Northern Lights for generations are also on the front lines of climate change, dealing with melting permafrost, changing wildlife patterns, and shifting weather systems. This connection between the aurora and climate change reveals something profound about our planet's interconnected systems. The same atmospheric layers that create the northern lights are also affected by greenhouse gases and changing weather patterns. Scientists studying long-term auroral records have found subtle shifts in the frequency and intensity of displays that correlate with broader atmospheric changes. It's a reminder that even the most ethereal phenomena are part of the complex web of systems that govern our world. The aurora also serves as a natural timekeeper, marking the passage of seasons in ways that transcend human calendars. For the indigenous peoples of the Arctic, the first appearance of the northern lights after the long summer months signals the beginning of winter's approach. The lights become more frequent and intense as the polar night deepens, reaching their peak during the darkest months when the sun barely rises above the horizon. There's something deeply moving about this celestial calendar. The way the aurora marks time not in hours or days, but in the great seasonal rhythms that have governed life in the Arctic for millennia. Modern life, with its artificial lights and climate-controlled environments, has largely disconnected us from these natural cycles. But the aurora remains, a reminder of the deeper rhythms that still pulse through our world. The study of historical auroral records has revealed fascinating patterns in solar activity over the centuries. Ancient chronicles from China, Europe, and other regions contain detailed accounts of unusual auroral displays, visible far from the polar regions. These historical observations, combined with modern satellite data, have helped scientists understand the long-term cycles of solar activity and their effects on Earth's magnetic environment. One of the most significant of these cycles is the solar maximum and minimum, an 11-year pattern of increasing and decreasing solar activity. During solar maximum, the Sun produces more flares and coronal mass ejections, leading to more frequent and intense auroral displays. During solar minimum, the aurora becomes less active, sometimes disappearing for days or weeks at a time. We're currently approaching the peak of solar cycle 25, which means the coming years should offer excellent opportunities for aurora viewing. But the Sun's activity varies on much longer timescales as well. The Maunder minimum, a period from roughly 1645 to 1715, when sunspot activity was extremely low, coincided with the Little Ice Age and dramatically reduced auroral activity. Historical records from that period describe years when the northern lights were rarely seen, even in regions where they're normally common. This connection between solar activity, climate, and the aurora illustrates the complex relationships that govern our planet's environment. The aurora has also played an unexpected role in the development of our understanding of Earth's upper atmosphere. Before the space age, the aurora was one of the few ways scientists could study the ionosphere, the layer of atmosphere where the lights occur. By analysing the colours and patterns of auroral displays, researchers could infer the composition and behaviour of gases at altitudes that were otherwise inaccessible. This research led to some surprising discoveries. Scientists found that the upper atmosphere is far more dynamic than previously thought, with temperatures and densities that vary dramatically with solar activity. The aurora revealed that space weather has real effects on Earth's atmosphere, influencing everything from radio propagation to satellite drag. These insights proved crucial when the first satellites were launched, as engineers needed to understand the environment their spacecraft would encounter. The aurora also helped scientists understand the shape and behaviour of Earth's magnetic field. By tracking the movement of auroral displays, researchers could map the invisible lines of magnetic force that surround our planet. They discovered that the magnetosphere is constantly changing, compressed and stretched by the solar wind like a soap bubble in a breeze. The aurora, in a sense, makes these invisible forces visible, providing a real-time display of the magnetic environment that protects us from space radiation. Modern aurora research has revealed that the phenomenon is far more complex than early scientists imagined. There are actually several different types of aurora, each created by different processes in the magnetosphere. The most common type, called discrete aurora, forms the familiar arcs and bands that most people associate with the northern lights. But there's also diffuse aurora, a faint glow that can cover large areas of the sky, and pulsating aurora, which appears to blink on and off like a cosmic strobe light. Each type of aurora tells a different story about the conditions in space. Discrete aurora forms when electrons are accelerated by strong electric fields in the magnetosphere. Diffuse aurora results from a more gentle process where particles gradually lose energy as they spiral down magnetic field lines. Pulsating aurora is created by interactions between electrons and very low-frequency radio waves in space, a process that scientists are still working to fully understand. The aurora also has a daily rhythm that reflects the rotation of Earth and the structure of the magnetosphere. The lights are most active around magnetic midnight when the observer is on the side of Earth opposite the Sun. This is because the magnetosphere's tail, where many of the processes that create the aurora occur, is stretched out on the night side of the planet. As Earth rotates, different regions move through this active zone, creating the nightly peak in auroral activity. But the aurora doesn't follow a simple schedule. Solar activity can trigger displays at any time, and the lights can appear suddenly and without warning. This unpredictability is part of what makes aurora watching so thrilling. You might spend hours scanning the sky with no sign of activity, only to have the entire northern horizon suddenly burst into colourful flames. The technology for observing and predicting the aurora has advanced dramatically in recent decades. Sophisticated computer models now simulate the complex interactions between the solar wind and Earth's magnetosphere, allowing scientists to forecast auroral activity with increasing accuracy. Real-time data from satellites and ground-based instruments is fed into these models, creating detailed predictions of where and when the aurora might appear. These forecasts have made aurora tourism more accessible, allowing travelers to plan trips with a better chance of seeing the lights. But they've also revealed the inherent chaos in the system. The magnetosphere is a complex, non-linear system where small changes in solar wind conditions can lead to dramatically different outcomes. A slight shift in the magnetic field orientation of the solar wind can mean the difference between a spectacular display and a quiet night. The aurora also varies with the seasons in ways that go beyond simple changes in darkness. The spring and autumn equinoxes tend to produce the most intense auroral activity, a phenomenon known as the Russell-McFerran effect. This happens because the orientation of Earth's magnetic field relative to the solar wind changes throughout the year, and the equinoxes represent times when the geometry is most favourable for magnetic reconnection, the process that triggers many auroral displays. This seasonal variation means that the best time to see the aurora depends on more than just darkness. While the lights can appear any time during the dark season, your chances are highest during the weeks around the equinoxes in March and September. This creates a natural rhythm to aurora watching, with peak seasons that draw enthusiasts from around the world to the polar regions. The aurora has also become a subject of citizen science, with thousands of amateur photographers and observers contributing to our understanding of the phenomenon. Social media has created a global network of aurora watchers who share real-time observations and images, providing scientists with a wealth of data about auroral activity. This crowdsourced approach has led to the discovery of new types of aurora and improved our understanding of how displays evolve over time. One of the most remarkable recent discoveries in aurora science is the identification of Steve, a phenomenon that was first recognized through citizen science observations. Steve appears as a narrow ribbon of purple light with a distinctive green picket fence structure below it. For years, photographers captured images of this phenomenon, but it wasn't until 2016 that scientists began to study it systematically. They discovered that Steve is created by a different process than the normal aurora, involving hot gas flowing through the magnetosphere at speeds of up to 6 kilometers per second. The discovery of Steve illustrates how much we still don't know about the aurora. Despite decades of research, new phenomena continue to be discovered, and our understanding of the complex processes that create the lights is still evolving. Each new satellite mission, each new ground-based instrument, each new theoretical model adds another piece to the puzzle. The aurora also serves as a natural laboratory for studying plasma physics, the science of ionized gases. The same processes that occur in the aurora happen throughout the universe, from the solar corona to the accretion disks around black holes. By studying the aurora, scientists gain insights into fundamental physical processes that govern much of the visible universe. The magnetosphere, in essence, is a natural plasma physics laboratory that we can study from our own backyard. The colours of the aurora tell a story about the composition of our atmosphere and the energy of the particles that create the lights. The familiar green glow comes from oxygen atoms excited by relatively low-energy electrons. The red aurora, often seen at the top of displays, comes from oxygen atoms excited by higher energy particles. The blue and purple colours come from nitrogen, while the rare yellow and orange hues result from a combination of gases under specific conditions. These colours aren't just beautiful, they're diagnostic tools that allow scientists to understand what's happening in the upper atmosphere. By analysing the spectrum of auroral light, researchers can determine the temperature, density, and composition of the gases where the aurora occurs. They can also infer the energy and type of particles that are creating the display, providing insights into the processes occurring far above in the magnetosphere. The aurora also has a three-dimensional structure that's far more complex than what we see from the ground. Satellite observations have revealed that auroral displays can extend hundreds of kilometers above the Earth's surface, forming vast curtains of light that undulate through space. What we see from the ground is just the bottom edge of these structures, like looking at the hem of a cosmic dress that extends far beyond our view. This three-dimensional nature of the aurora becomes apparent when you view it from different locations. Observers separated by just a few hundred kilometers can see dramatically different displays, even though they're looking at the same phenomenon. The aurora's structure changes with altitude, creating a complex tapestry of light that reveals itself differently depending on your vantage point. The aurora also has a memory of sorts, with displays often showing patterns that reflect the history of magnetic activity. A single auroral display might be the result of particles that were injected into the magnetosphere hours or even days earlier, gradually making their way down magnetic field lines to create the lights we see. This means that the aurora we observe tonight might be telling the story of solar activity that occurred yesterday or last week. The study of the aurora has also revealed the importance of Earth's magnetic field in protecting our planet from harmful radiation. Without this invisible shield, the solar wind would gradually strip away our atmosphere, much as it appears to have done to Mars billions of years ago. The aurora, in a sense, is a visible reminder of the protection that our magnetic field provides, a beautiful display of the forces that keep our planet habitable. As we continue to explore the cosmos and search for life elsewhere in the universe, the aurora serves as a benchmark for understanding the conditions that might exist around other worlds. Planets with strong magnetic fields and active atmospheres might host their own auroral displays, while those without such protection might be barren and lifeless. The aurora, therefore, becomes not just a beautiful phenomenon, but a potential signature of habitability that we might one day detect around distant worlds. The future of aurora research holds exciting possibilities. New satellite missions are planned that will study the aurora with unprecedented detail, while advances in computing power will allow for more sophisticated modelling of magnetospheric processes. Ground-based instruments are becoming more sensitive and capable of detecting ever fainter auroral phenomena. The combination of these advances promises to unlock new secrets about the aurora and the complex system that creates it. But perhaps the most important aspect of the aurora is not scientific, but spiritual. In our modern world, filled with artificial lights and electronic distractions, the aurora offers a connection to something larger than ourselves. It reminds us that we live on a planet that is part of a vast dynamic system stretching from the sun to the edge of the solar system. The aurora whispers to us of cosmic forces and ancient rhythms, of the delicate balance that makes life possible, and of the beauty that emerges when we take the time to look up at the night sky. The northern lights continue to dance across the polar skies tonight, just as they have for billions of years before us and will for billions of years after we're gone. They are a reminder that the universe is alive with energy and motion, that even in the coldest, darkest places, there can be warmth and light. And perhaps, in these quiet moments when we pause to contemplate the aurora, we find something of that same light within ourselves, a recognition that we too are part of this vast, beautiful, ever-changing cosmos. The aurora has taught us that Earth is not a solitary wanderer in space, but rather a dynamic participant in the grand conversation between planets and stars. Every photon of auroral light carries with it the story of this conversation, a message written in the language of charged particles and magnetic fields, translated into the colours and patterns that paint our northern skies. What's particularly enchanting about the aurora is how it connects us to time itself. The light we see tonight began its journey as nuclear fusion in the sun's core, a process that took hundreds of thousands of years to work its way from the solar interior to the surface. From there, it travelled as solar wind for days or weeks before encountering Earth's magnetic field. The particles that create the aurora might have been captured and stored in our magnetosphere for hours, days, or even longer before finally cascading down into our atmosphere to create the display we witness. In this sense, watching the aurora is like reading a cosmic diary, each shimmer and pulse recording events that happened across vast distances and spans of time. The green curtain rippling overhead might be telling the story of a solar flare that erupted when you were having your morning coffee three days ago. The sudden brightening of the display could be the signature of a coronal mass ejection that left the sun while you were sleeping last week. There's something deeply humbling about this temporal connection. The aurora reminds us that the present moment is not isolated, but connected to a vast web of cause and effect that stretches across the solar system. We are not separate from the cosmic processes that surround us, but intimately connected to them, participants in a dance that began long before our species existed and will continue long after we're gone. The indigenous peoples of the Arctic understood this connection intuitively. Their stories and legends about the aurora often emphasize the relationship between the lights and the ancestors, the way the present is connected to the past and the future. They saw in the aurora not just a beautiful display, but a reminder of continuity, of the eternal cycles that govern both human life and the natural world. Modern science has given us new vocabulary to describe these connections, terms like plasma physics and magnetospheric dynamics, but the fundamental truth remains the same. The aurora is a bridge between worlds, a visible manifestation of invisible forces, a reminder that the boundary between Earth and space is not a wall, but a permeable membrane through which energy and matter flow constantly. For those who have experienced the aurora firsthand, there's often a moment of recognition, a sudden understanding that you are witnessing something profound. It might come when you first see the lights appear on the horizon, a faint green glow that gradually intensifies until it fills the entire sky. Or it might happen during a particularly intense display when the aurora seems to pulse with its own heartbeat, when the lights dance with such energy that they seem almost alive. These moments of recognition are deeply personal, yet they connect us to the millions of other people who have stood beneath the aurora throughout history. The same lights that inspired ancient myths and legends continue to move modern observers to tears. The aurora transcends cultural boundaries, speaking to something fundamental in the human spirit that responds to beauty, mystery, and the vast scales of cosmic time and space. The aurora also teaches us about resilience and adaptation. Our planet has been bombarded by solar radiation for billions of years, yet life has not only survived but thrived. The magnetic field that creates the aurora has protected Earth's atmosphere from being stripped away by the solar wind, while the same charged particles that could be harmful instead create one of nature's most beautiful displays. It's a reminder that what might seem like a hostile environment can be transformed into something life-giving and beautiful. This lesson extends beyond planetary science to our daily lives. Just as Earth transforms the potentially harmful solar wind into the beautiful aurora, we too can learn to transform the challenges we face into opportunities for growth and beauty. The aurora shows us that protection and beauty can coexist, that the same forces that threaten can also create wonder if we have the right perspective and the proper defences. The aurora also reveals the importance of darkness in our lives. In our modern world, we often see darkness as something to be eliminated, filled with artificial light and electronic screens. But the aurora reminds us that darkness is not the absence of light, but the canvas on which the most beautiful lights can be painted. Without the darkness of the polar night, the aurora would be invisible, overwhelmed by the brightness of the sun. There's a metaphor here for our inner lives as well. Sometimes we need periods of darkness, times of quiet and reflection, to see the subtle lights that are always present, but often hidden by the noise and brightness of our daily routines. The aurora teaches us that some of the most beautiful experiences require patience, stillness, and the willingness to sit with uncertainty while we wait for the right conditions to reveal themselves. The predictability and unpredictability of the aurora also offer lessons about the nature of natural systems. While we can forecast general trends in auroral activity, we cannot predict exactly when or where the most spectacular displays will occur. This combination of pattern and chaos is characteristic of complex systems throughout nature, from weather patterns to ecosystem dynamics to the behavior of financial markets. The aurora teaches us to be prepared for beauty, to position ourselves in the right place at the right time, but also to remain open to surprise. The most memorable auroral displays are often the unexpected ones, the nights when conditions seemed unfavourable but the lights appeared anyway, or when a routine observation session suddenly exploded into a spectacular show that exceeded all expectations. This balance between preparation and openness is perhaps one of the most valuable lessons the aurora can teach us. We can study the science, check the forecasts, and travel to the best locations. But ultimately, we must surrender to the mystery, accepting that some of the most beautiful experiences in life cannot be forced or controlled, only witnessed with gratitude when they occur. The aurora also connects us to the broader story of scientific discovery. Every time we look up at the northern lights, we're participating in a tradition of observation and wonder that stretches back to the earliest human civilizations. The same curiosity that led ancient peoples to create stories about the aurora drives modern scientists to launch satellites and build complex computer models to understand the phenomenon. This continuity of human curiosity is one of our species' most beautiful characteristics. We are not content to simply witness beauty. We want to understand it, to place it in context, to share our discoveries with others. The aurora has been a catalyst for this kind of inquiry for centuries, inspiring advances in physics, chemistry, and space science that have applications far beyond atmospheric research. The study of the aurora has also taught us about the importance of international cooperation in science. The aurora is a global phenomenon that requires observations from multiple locations and perspectives to fully understand. Scientists from different countries and cultures have worked together to build the networks of instruments and share the data necessary to study the aurora comprehensively. This cooperative spirit reflects the aurora itself, which transcends national boundaries and political divisions. The same magnetic field lines that guide auroral particles over Alaska also extend over Canada, Greenland, and Siberia. The aurora reminds us that we share one planet, one magnetosphere, one relationship with the sun that affects us all, regardless of where we live or what language we speak. The aurora also serves as a reminder of the importance of preserving dark skies. As artificial lighting spreads across the planet, there are fewer and fewer places where the aurora can be seen clearly. Light pollution doesn't just hide the stars, it also obscures the subtle beauty of the aurora, making it harder for future generations to experience this natural wonder. The growing movement to protect dark skies recognizes that darkness is not something to be feared, but something to be cherished. Dark sky reserves and national parks are being established around the world, creating sanctuaries where the aurora and other astronomical phenomena can be experienced as they were meant to be seen. These efforts ensure that future generations will have the opportunity to stand beneath the dancing lights and feel the same sense of wonder that has inspired humans for millennia. The aurora also teaches us about the value of patience and persistence. Aurora watching is not a hobby for those who need instant gratification. It requires long hours in cold conditions, often with no guarantee of seeing anything spectacular. But those who persist are occasionally rewarded with displays of such beauty that they justify all the waiting and discomfort. This patience is becoming increasingly rare in our fast-paced world, where we expect immediate results and constant stimulation. The aurora offers a different rhythm, one that connects us to the deeper patterns of nature and the cosmos. It teaches us that some of the most meaningful experiences require time to unfold, that beauty cannot be rushed, and that the act of waiting itself can be a form of meditation. The aurora also reminds us of the importance of being present in the moment. When the lights begin to dance, all other concerns fade away. There's no past or future, only the immediate experience of witnessing something extraordinary. This presence is a gift that the aurora gives to those who take the time to observe it, a reminder that the most profound experiences often come when we stop thinking about our problems and simply allow ourselves to be amazed. The colours of the aurora have their own language, a vocabulary of reds and greens and blues that speaks to something deep in human consciousness. These colours are not arbitrary, but are determined by the fundamental properties of atoms and molecules, the same quantum mechanical processes that govern the behaviour of matter throughout the universe. In the aurora, we see the invisible laws of physics made visible, the abstract concepts of science transformed into tangible beauty. The green glow of oxygen has become the signature colour of the aurora, the shade that most people associate with the northern lights. But this green is not just any green, it's a specific wavelength of light that corresponds to a particular energy transition in the oxygen atom. When you see that familiar green curtain rippling across the sky, you're witnessing quantum mechanics in action, the same principles that govern the behaviour of electrons in computer chips and solar cells. The rarer red auroras, often seen at the top of displays, tell a different story. These are created by oxygen atoms at higher altitudes, where the atmosphere is thinner and the particles have different energy levels. The red light represents a different quantum transition, one that requires different conditions to occur. In a sense, the colours of the aurora are a diagnostic tool, telling us about the composition and behaviour of the upper atmosphere. The blue and purple hues contributed by nitrogen add another layer to the aurora's palette. Nitrogen is more abundant in our atmosphere than oxygen, but it produces auroral colours that are often fainter and less easily seen by the human eye. These colours become more prominent in photographs where long exposures and sensitive cameras can capture wavelengths that our eyes might miss. The aurora also has a temporal dimension that extends beyond the immediate display. The particles that create the lights often follow complex paths through the magnetosphere, bouncing back and forth between the northern and southern hemispheres multiple times before finally entering the atmosphere. This means that a single injection of particles from the solar wind can create multiple auroral displays over the course of several days, each one slightly different as the particles lose energy and change their trajectories. This temporal complexity means that the aurora has a kind of memory, with each display influenced by the history of magnetic activity that preceded it. The aurora we see tonight might be the culmination of processes that began days or weeks ago, making each display a unique combination of current conditions and historical influences. The aurora also varies with the solar cycle, the 11-year pattern of increasing and decreasing solar activity. During solar maximum, when the sun is most active, auroral displays are more frequent and intense. During solar minimum, the aurora becomes more elusive, sometimes disappearing for extended periods. This cycle connects the aurora to the broader patterns of solar behaviour, making it a visible indicator of our star's activity. We are currently in an interesting phase of the solar cycle, with activity gradually increasing toward the next solar maximum expected around 2025. This means that the coming years should offer excellent opportunities for aurora viewing, with more frequent displays and better chances of seeing the lights at lower latitudes than usual. The aurora also serves as a natural time capsule, preserving information about past solar activity in the geological record. When particularly intense auroral displays occur, they can affect the production of certain isotopes in the atmosphere, which then become incorporated into ice cores and tree rings. By studying these natural archives, scientists can reconstruct the history of solar activity and auroral displays going back thousands of years. These historical records reveal that the aurora has been a constant presence throughout human history, but with significant variations in intensity and frequency. Periods of high solar activity have produced spectacular auroral displays visible far from the polar regions, while quiet periods have made the lights rare even in their usual haunts. These variations remind us that the aurora is not a static phenomenon but part of a dynamic system that changes over time. The aurora also connects us to the future, serving as a natural laboratory for understanding space weather and its effects on our increasingly technological society. As we become more dependent on satellites, GPS systems, and electronic communications, understanding the aurora and the space weather that creates it becomes increasingly important for maintaining our modern way of life. The same charged particles that create the beautiful aurora can also disrupt satellite operations, interfere with radio communications, and even cause power outages. The Great Magnetic Storm of 1989 caused a 9-hour blackout in Quebec, while more recent events have disrupted airline communications and GPS systems. As our technology becomes more sophisticated and more vulnerable to space weather, the aurora serves as a visible reminder of the invisible forces that can affect our daily lives. But rather than seeing this as a threat, we can view it as an opportunity to develop more resilient technologies and better understanding of the space environment. The aurora teaches us that we are part of a larger system, connected to the sun and the cosmos in ways that our ancestors could never have imagined. By studying the aurora, we learn not just about a beautiful natural phenomenon, but about our place in the universe and our responsibility to understand and protect the systems that sustain us. The aurora also reminds us of the importance of international cooperation in addressing global challenges. Space weather affects the entire planet, and understanding it requires observations and data from around the world. The networks of scientists and instruments that study the aurora represent a model for the kind of international cooperation that will be necessary to address other global challenges, from climate change to pandemic preparedness. As we look to the future, the aurora will continue to serve as both a source of wonder and a subject of scientific study. New technologies will allow us to observe the aurora with ever greater detail and precision, while advances in computer modelling will help us understand the complex processes that create the lights. But no matter how much we learn about the aurora, it will always retain its capacity to inspire awe and wonder in those who witness it. The aurora also serves as a bridge between the scientific and the spiritual, between the rational and the mystical. While we can explain the physics of how the aurora is created, we cannot fully explain why it moves us so deeply or why it has inspired so many stories and legends throughout human history. There is something about the aurora that transcends scientific explanation, something that speaks to a deeper part of human nature that recognizes beauty and meaning in the natural world. Perhaps this is the aurora's greatest gift to us, not just the knowledge it provides about plasma physics and space weather, but the reminder that we live in a universe of extraordinary beauty and complexity. The aurora teaches us that even in the coldest, darkest places, there can be warmth and light, that the same forces that seem threatening can also create wonder, and that the boundary between science and spirit is not as clear as we sometimes imagine. In these quiet moments, as we contemplate the aurora dancing across the northern sky, we are reminded of our connection to something larger than ourselves. We are part of a story that began with the formation of the solar system and will continue long after we are gone. The aurora is both a window into this larger story and a reminder of our place within it, a beautiful manifestation of the invisible forces that shape our world and our lives. The Northern Lights continue their eternal dance tonight, just as they have for billions of years, just as they will for billions more. They are a reminder that the universe is alive with energy and motion, that beauty exists on scales both vast and intimate, and that sometimes the most profound truths are written not in books but in the sky itself, in languages of light and colour that speak directly to the human heart. The aurora has also revealed to us the remarkable fact that our planet breathes with the rhythm of space itself. Every 24 hours, as Earth rotates through the solar wind, our magnetosphere expands and contracts like lungs drawing breath. During the day, when our planet faces the sun, the solar wind compresses the magnetosphere on the sunward side. At night, as we turn away from our star, the magnetosphere stretches out into a long tail that extends far beyond the moon's orbit. This daily breathing creates its own patterns in auroral activity. The lights tend to be most active around magnetic midnight, when the observer is positioned in Earth's magnetic shadow, where the stretched magnetotail undergoes complex reconnection events that send particles cascading down toward the poles. It's rather like standing at the perfect spot to watch cosmic fireworks, where the geometry of space and time aligns to create the most spectacular show. But the aurora doesn't simply follow predictable patterns. It has moods, temperaments that shift with the subtle changes in solar wind conditions. A slight rotation in the magnetic field carried by the solar wind can transform a quiet night into a spectacular display. Or conversely, turn what should have been a brilliant show into a disappointing whisper of light on the horizon. This sensitivity to conditions reminds us that the aurora is not a machine but a living system, responding to the ever-changing conversation between Earth and space. The particles that create the aurora follow paths of extraordinary complexity through our magnetosphere. They don't simply fall straight down from space like rain, but instead spiral along magnetic field lines, bouncing back and forth between the northern and southern hemispheres in a cosmic pinball game that can last for hours or days. Some particles make dozens of trips between the poles before finally colliding with atmospheric molecules to create the lights we see. This bouncing motion, called mirroring, occurs because Earth's magnetic field becomes stronger closer to the poles, creating magnetic bottles that trap particles and send them ricocheting back toward the opposite hemisphere. The result is that a single burst of particles from the solar wind can create multiple auroral displays, with the lights appearing first in one hemisphere, then the other, then back again, like a slow-motion tennis match played across the entire planet. The aurora also has what scientists call substorms, sudden intensifications that can transform a quiet arc of light into a spectacular explosion of colour and motion. These substorms are triggered by changes in the configuration of Earth's magnetic field, often occurring when magnetic field lines in the magnetotail suddenly snap and reconnect, releasing stored energy like a cosmic rubber band snapping back into place. During a substorm, the aurora can brighten dramatically in just minutes, expanding poleward and developing the rapid motion and complex structure that makes for the most memorable displays. The lights might pulse with increasing frequency, develop vertical rays that seem to reach toward the zenith, or break up into rapidly moving patches of light that dance across the sky like celestial sprites. These substorms reveal the dynamic nature of our planet's magnetic environment. Far from being a static shield, the magnetosphere is constantly changing, storing and releasing energy in response to the variable solar wind. The aurora serves as a visible indicator of this activity, a real-time display of the invisible forces at work high above our heads. The study of auroral substorms has also revealed the interconnected nature of space weather. A substorm that creates beautiful lights over Alaska might simultaneously disrupt radio communications in Europe or cause navigation problems for ships in the Arctic Ocean. The same magnetic field lines that guide auroral particles also channel electrical currents that can induce voltages in power lines and pipelines thousands of kilometers away. This global connectivity of space weather phenomena reminds us that the aurora is not an isolated curiosity, but part of a vast system that affects the entire planet. The beauty we see in the sky is intimately connected to the technological challenges we face on the ground, making the study of the aurora both aesthetically rewarding and practically important. The aurora also varies with altitude in ways that create a three-dimensional tapestry of light invisible from any single vantage point. The green oxygen emissions that we see most commonly occur at altitudes of about 100 to 200 kilometers above the surface. The red oxygen emissions happen higher up, around 300 to 400 kilometers, while the blue and purple nitrogen emissions can occur at various altitudes depending on the energy of the incoming particles. This vertical structure means that the aurora has depth, extending from just above the dense atmosphere to heights where the air is so thin that molecules are separated by vast distances. Pilots flying at high altitudes sometimes report seeing the aurora both above and below them, a surreal experience that emphasizes the three-dimensional nature of the phenomenon. The altitude structure of the aurora also tells us about the energy of the particles creating the display. Higher energy particles penetrate deeper into the atmosphere before colliding with air molecules, creating emissions at lower altitudes. Lower energy particles are stopped higher up, creating the red emissions we sometimes see at the top of auroral displays. In this way, the vertical distribution of auroral colours serves as a natural spectrometer, revealing the energy spectrum of the particles raining down from space. Satellites observing the aurora from above have revealed structures that are completely invisible from the ground. They've discovered that auroral arcs are actually narrow ribbons of light, sometimes only a few kilometers wide, but hundreds of kilometers long. From space, these ribbons appear to be aligned with the direction of the magnetic field, creating patterns that look remarkably like iron filings arranged around a magnet. These satellite observations have also revealed that the aurora extends much higher into space than previously thought. While the visible aurora that we see from the ground occurs below about 400 kilometers altitude, satellite instruments have detected auroral emissions extending up to 1,000 kilometers or more above the surface. This high-altitude aurora is usually too faint to see with the naked eye, but it represents a significant portion of the total energy deposited by auroral particles. The aurora also has a relationship with the moon that adds another layer of complexity to its behaviour. While the moon doesn't directly affect the aurora the way it affects ocean tides, the lunar cycle does seem to influence auroral activity in subtle ways. Some researchers have found statistical correlations between the phase of the moon and the frequency of certain types of auroral displays, though the mechanism behind this correlation remains unclear. One possibility is that the moon's gravitational field affects the shape of Earth's magnetosphere in ways that influence how solar wind particles enter and circulate within it. Another theory suggests that the moon might affect the neutral atmosphere at auroral altitudes, changing the efficiency with which incoming particles create visible light. These are active areas of research where the full story has yet to be told. The aurora also interacts with atmospheric waves and weather patterns in ways that scientists are still discovering. The upper atmosphere where the aurora occurs is connected to the lower atmosphere through a complex web of dynamical processes. Large-scale weather patterns can influence the temperature and density of the upper atmosphere, which in turn affects how auroral particles interact with atmospheric molecules. Climate change is beginning to have measurable effects on the upper atmosphere as well. As greenhouse gases warm the lower atmosphere, they actually cause the upper atmosphere to cool and contract. This cooling changes the altitude at which auroral emissions occur and may affect the colours and intensity of the displays. It's a reminder that even phenomena that seem completely removed from human activities are connected to the global changes we're causing in Earth's climate system. The aurora has also been affected by human activities in more direct ways. The explosion of nuclear weapons in the upper atmosphere during the 1950s and 1960s created artificial auroras by injecting high-energy particles into the magnetosphere. These experiments, while scientifically interesting, demonstrated the fragility of the natural systems that create the aurora and the potential for human activities to disrupt them. More recently, powerful radio transmitters used for communication and research have been found to create artificial auroral displays on a smaller scale. These human-made auroras are usually much fainter than natural displays, but they demonstrate our growing ability to influence the space environment around our planet. As our technological capabilities grow, we must be mindful of the potential impacts on the natural phenomena that inspire and sustain us. The aurora also serves as a natural laboratory for studying atmospheric chemistry. The high-energy particles that create the aurora also drive chemical reactions in the upper atmosphere, creating and destroying various atmospheric constituents. During particularly intense auroral displays, these chemical changes can be significant enough to affect the global atmospheric composition, at least temporarily. For example, auroral particles can create nitrogen oxides in the upper atmosphere, which then react with ozone molecules. During major geomagnetic storms, this process can create temporary holes in the ozone layer over the polar regions. While these effects are usually short-lived, they demonstrate the interconnected nature of atmospheric processes and the far-reaching impacts of space weather. The aurora has also been linked to phenomena in the lower atmosphere, including possible effects on weather patterns and cloud formation. Some researchers have suggested that the electrical currents associated with auroral activity might influence atmospheric electricity in ways that affect weather systems. These connections are still being investigated, but they hint at the possibility that space weather and terrestrial weather might be more closely linked than previously thought. The study of historical auroral records has revealed fascinating patterns in long-term climate variations. Periods of low solar activity, when auroras were rare, often coincided with cooler global temperatures, while periods of high solar activity correlated with warmer conditions. While the aurora itself doesn't cause climate change, it serves as a proxy for solar activity, which does have measurable effects on Earth's climate. These historical correlations have helped scientists understand the role of solar variability in natural climate change, providing important context for understanding current human-caused climate change. The aurora, in this sense, serves as a natural archive of solar-terrestrial interactions, preserving information about past space weather in the written records of human observers. The aurora also varies with geographic location in ways that reflect the complex structure of Earth's magnetic field. While the aurora is most commonly seen in a ring around each magnetic pole, this auroral oval is not perfectly circular or centered on the geographic poles. Instead, it's offset and elongated in ways that reflect the fact that Earth's magnetic field is not perfectly dipolar. The magnetic North Pole, for example, is currently located in the Arctic Ocean north of Canada, but it's moving steadily towards Siberia at a rate of about 50 kilometers per year. This movement affects the location of the auroral oval, gradually shifting the regions where the aurora is most commonly seen. Over human timescales, these changes are relatively small, but over geological time, they can be significant. The aurora also exhibits what scientists call magnetic local time effects, meaning that the characteristics of the display depend not just on your geographic location, but on your position relative to the magnetic field structure. Observers at different magnetic local times often see very different types of auroral activity, even when they're at similar magnetic latitudes. This magnetic coordinate system provides a more accurate way to predict and understand auroral activity than simple geographic coordinates. The aurora has also been found to have effects on the ionosphere that extend far beyond the visible display. The same particles that create the lights also enhance the ionization of the upper atmosphere, affecting radio wave propagation across large regions. During major auroral displays, these ionospheric effects can be detected thousands of kilometers away from the visible aurora, demonstrating the far-reaching influence of space weather phenomena. These ionospheric effects have practical implications for communication systems, navigation, and surveillance. Military and civilian radar systems can be affected by auroral activity, while GPS accuracy can be degraded over large areas during geomagnetic storms. Understanding these effects has become increasingly important as our society becomes more dependent on space-based technologies. The aurora also exhibits periodic variations that reflect the complex dynamics of the magnetosphere. In addition to the daily and seasonal cycles, the aurora shows variations on timescales of minutes to hours that correspond to different types of magnetospheric processes. Some of these variations are regular and predictable, while others appear to be chaotic and random. The study of these temporal variations has revealed that the magnetosphere behaves like a complex dynamical system, with multiple interacting components that can exhibit both ordered and chaotic behavior. The aurora serves as a visible manifestation of this complexity, displaying patterns that range from simple and regular to intricate and unpredictable. One of the most intriguing aspects of auroral dynamics is the occurrence of what scientists call auroral kilometric radiation, intense radio emissions that accompany many auroral displays. These radio waves, which have wavelengths of about a kilometre, are generated by the same electron acceleration processes that create the visible aurora. While we can't hear these radio emissions directly, they can be detected by specialized instruments and provide important information about the processes occurring in the auroral acceleration region. The aurora also exhibits conjugacy effects, meaning that auroral displays in the northern hemisphere are often mirrored by similar displays in the southern hemisphere. This occurs because the same magnetic field lines that guide particles toward the North Pole also guide them toward the South Pole. However, the conjugacy is not perfect, and there can be significant differences between northern and southern auroral displays due to seasonal effects and asymmetries in Earth's magnetic field. The study of auroral conjugacy has required international cooperation between researchers in the Arctic and Antarctic, leading to coordinated observation campaigns that span both hemispheres. These studies have revealed subtle but important differences between northern and southern auroral activity and have helped scientists understand how seasonal variations in atmospheric composition and solar illumination affect auroral processes. The aurora also serves as a natural indicator of the health of Earth's magnetosphere. Changes in auroral activity patterns can signal important changes in the magnetic field or in the way it interacts with the solar wind. Long-term studies of auroral occurrence have revealed secular changes that may be related to ongoing changes in Earth's magnetic field, including the gradual weakening of the field and the movement of the magnetic poles. These long-term changes in auroral activity provide important clues about the evolution of Earth's magnetic field and its ability to protect us from space radiation. While the magnetic field has reversed many times in Earth's history, and life has survived these reversals, understanding how such changes affect the aurora and the upper atmosphere helps us prepare for potential future changes. The aurora also interacts with other atmospheric phenomena in complex ways. For example, during winter in the polar regions, the aurora occurs in the same altitude range as polar stratospheric clouds, leading to interesting interactions between auroral particles and cloud particles. These interactions can affect both the appearance of the aurora and the properties of the clouds, creating feedback effects that are still being studied. The aurora has also been found to influence the formation and evolution of atmospheric gravity waves, large-scale oscillations in the atmosphere that can transport energy and momentum over vast distances. Auroral heating of the upper atmosphere can generate these waves, which then propagate downward and may affect weather patterns in the lower atmosphere. These connections between the aurora and atmospheric dynamics represent an active area of research with implications for our understanding of atmospheric coupling processes. As we've explored the many facets of the aurora, from its fundamental physics to its cultural significance, we've seen that this phenomenon touches nearly every aspect of the Earth-space environment. The aurora is simultaneously a thing of beauty and a scientific tool, a source of wonder and a practical concern, a link to our past and a window into our future. The aurora reminds us that we live on a dynamic planet, in a dynamic solar system, where change is the only constant and where beauty often emerges from the complex interactions of seemingly simple forces. As we continue to study and appreciate the aurora, we deepen our understanding not just of this particular phenomenon, but of the intricate web of connections that link our planet to the cosmos. Tonight, as the aurora dances across the northern sky, it carries with it the stories of solar flares and magnetic storms, of ancient legends and modern discoveries, of the delicate balance that makes our world habitable, and the cosmic forces that shape our destiny. In its shimmering curtains of light, we see reflected our own journey of discovery, our endless quest to understand our place in the universe and our profound connection to the stars that gave us birth. The Northern Lights continue their eternal performance, indifferent to our presence, yet somehow enhanced by our witness. They remind us that the universe is far stranger and more beautiful than we can easily comprehend, full of phenomena that challenge our understanding and inspire our imagination. In the aurora, we find both the humility that comes from recognizing our small place in the cosmic order and the wonder that makes that place meaningful and precious. As the lights fade with the approaching dawn, they leave behind not just memories, but questions, not just satisfaction, but curiosity about what other secrets the universe might reveal to those patient enough to watch and wonder. The aurora is both an ending and a beginning, a moment of beauty that connects us to the eternal dance of matter and energy that shapes our world and our lives. In the gentle hours before dawn, when the aurora begins to fade but its memory lingers in both sky and mind, we find ourselves contemplating something rather profound about the nature of observation itself. You see, the aurora doesn't simply exist as a static phenomenon waiting to be discovered. In many ways, it exists in relationship with those who witness it, changing subtly based on the very act of being observed. Consider for a moment the curious fact that no two people ever see exactly the same aurora, even when standing side by side. This isn't merely poetic license, but scientific reality. The aurora occurs at such heights and spans such vast distances that your precise location, the angle of your view, and even the sensitivity of your particular eyes all contribute to creating a unique experience that belongs to you alone. The aurora you see tonight has never been seen before and will never be seen again in quite the same way. This personal nature of auroral observation extends beyond simple geometry. The aurora responds to the observer's patience, revealing more of its secrets to those willing to stand quietly in the cold, allowing their eyes to adjust fully to the darkness. Many first-time aurora watchers make the mistake of looking for something as bright as a neon sign, only to miss the subtle green glow that's been dancing on the horizon for hours. The aurora rewards those who approach it with the right expectations, not demanding, but receptive, not hurrying, but willing to wait. There's also the matter of auroral memory, both in the scientific sense and in the deeply personal one. The particles that create tonight's display carry with them the memory of their journey from the sun, while the magnetic field that guides them remembers the history of countless solar storms that have shaped its current configuration. But we observers bring our own memories to the experience as well, memories of other nights spent beneath the stars, other moments when we felt connected to something larger than ourselves. These personal memories become part of the aurora's story in ways that meteorology textbooks rarely mention. The grandmother in northern Finland, who has watched the lights dance for 70 winters, brings a different perspective to each display than the tourist experiencing the aurora for the first time. Her eyes have learned to read the subtle signs that predict when the lights might brighten, when they might develop vertical structure, when they might suddenly explode across the entire sky. This accumulated wisdom becomes part of the aurora's folklore, passed down through generations of northern peoples who have made the lights a part of their cultural DNA. The aurora also teaches us about the relationship between expectation and wonder. In our age of instant gratification and carefully curated experiences, the aurora stands as a reminder that some things cannot be scheduled, packaged, or guaranteed. You can travel thousands of kilometers to the perfect location, arrive during the optimal season, check all the forecasts and conditions, and still spend your nights looking up at empty skies. The aurora doesn't care about your vacation schedule or your travel budget. Yet this unpredictability is precisely what makes each auroral sighting so precious. When the lights do appear, when they begin their dance across the darkness, there's an element of gift about the experience that no amount of planning can create. The aurora gives itself freely to those who position themselves to receive it, but it cannot be forced, purchased, or commanded. In a world where so much can be controlled and predicted, the aurora remains beautifully, stubbornly wild. This wildness extends to the aurora's relationship with technology. While satellites and computer models can predict general conditions favorable for auroral activity, they cannot tell you exactly when or where the most spectacular displays will occur. The aurora exists at the boundary between the predictable and the chaotic, where small changes in solar wind conditions can lead to dramatically different outcomes. It's a reminder that despite all our technological sophistication, nature still holds secrets that resist complete understanding. The aurora also exists in a unique temporal space that challenges our normal relationship with time. When you're watching an active display, minutes can feel like hours as you become completely absorbed in the dance of light overhead. The aurora operates on its own timeline, sometimes remaining stable for hours, other times changing so rapidly that you can barely keep up with the transformations. This auroral time seems to exist outside the normal flow of human schedules and deadlines, creating a pocket of eternity in the midst of our hurried lives. Photography has complicated this temporal relationship in interesting ways. While cameras can capture auroral colours and structures that are too faint for the eye to see clearly, they also freeze motion that is essentially dynamic. The aurora is not a thing, but a process, not a static image, but a continuous performance. Long exposure photographs can create stunning images that compress minutes of auroral motion into a single frame, but they inevitably lose something of the aurora's essential character as a phenomenon in constant flux. This tension between capturing and experiencing the aurora reflects a broader question about our relationship with natural phenomena in the digital age. Do we risk losing something essential when we view the aurora primarily through screens and photographs rather than direct observation? While technology certainly helps us understand and predict the aurora, there's something irreplaceable about the immediate, unmediated experience of standing beneath the lights with no barrier between yourself and the cosmic forces at play. The aurora also challenges our normal categories of indoor and outdoor experience. When you're watching the aurora, you're simultaneously aware of being on Earth's surface and of participating in processes that extend far into space. The lights overhead connect you directly to events occurring hundreds of kilometers above and millions of kilometers away. In that moment, the usual boundaries between terrestrial and cosmic, between human scale and astronomical scale, begin to blur. This boundary-blurring quality of the aurora may explain why it has such a powerful effect on human consciousness. We are beings adapted to operate within certain spatial and temporal scales, yet the aurora invites us to expand our awareness to encompass vast distances and time spans. When we watch the aurora, we're not just observing a pretty light show, but participating in a cosmic event that connects us to the fundamental forces that govern the universe. The aurora also serves as a natural meditation on the relationship between science and spirituality. While we can explain the physical processes that create the lights in remarkable detail, this scientific understanding doesn't diminish the aurora's capacity to inspire awe and wonder. If anything, knowing about magnetic field lines and particle acceleration makes the aurora more remarkable, not less. The fact that such beauty emerges from the interplay of invisible forces operating according to mathematical laws seems almost miraculous. This compatibility between scientific understanding and aesthetic appreciation represents one of the aurora's greatest gifts to human culture. The aurora demonstrates that knowledge and wonder can coexist, that understanding how something works doesn't drain it of mystery or beauty. The more we learn about the aurora, the more remarkable it becomes, revealing layers of complexity and elegance that reward both scientific study and contemplative observation. The aurora also exists in a special relationship with silence. Unlike most spectacular natural phenomena, which announce themselves with sound, the aurora performs its dance in complete silence. This silence is not empty but full, charged with the energy of invisible processes occurring overhead. When you're watching the aurora, you become acutely aware of sound, of your own breathing, of the subtle noises of the night around you. The silence of the aurora creates a space for reflection and introspection that's increasingly rare in our noisy world. This quality of auroral silence has influenced the ways different cultures have interpreted the lights. Some indigenous traditions speak of being able to hear the aurora, describing subtle crackling or whispering sounds that accompany the most intense displays. Whether these sounds are real or imagined remains a subject of scientific debate, but their presence in folklore suggests something important about the human need to find voice in the aurora's silence. The aurora also teaches us about the relationship between vulnerability and beauty. The same thin atmosphere that allows us to see the aurora also makes the polar regions where it occurs some of the most challenging environments on Earth. To witness the aurora, you must expose yourself to cold, darkness, and isolation. You must make yourself vulnerable to the elements in ways that our comfortable modern lives rarely require. This vulnerability becomes part of the experience, heightening your awareness and making the eventual appearance of the lights feel like a reward for your courage and patience. This connection between vulnerability and reward reflects a deeper truth about many of life's most meaningful experiences. The aurora reminds us that some things can only be encountered by stepping outside our comfort zones, by accepting uncertainty and discomfort as part of the price of wonder. The aurora doesn't come to you, you must go to it, and in that journey lies much of its transformative power. The aurora also exists in dialogue with darkness in ways that illuminate the relationship between light and shadow in human experience. The aurora can only be seen against the backdrop of a truly dark sky, making it dependent on the very darkness that many people fear or try to avoid. The aurora teaches us that darkness is not the enemy of light, but its collaborator, the stage on which light's most beautiful performances can unfold. This partnership between light and dark in the aurora offers a metaphor for understanding difficult periods in our own lives. Just as the aurora requires darkness to be visible, perhaps our most illuminating experiences require us to pass through periods of uncertainty or challenge. The aurora suggests that beauty and meaning can emerge from conditions that initially seem barren or threatening. The aurora also demonstrates the importance of perspective in shaping experience. The same magnetic storm that creates beautiful auroral displays can also disrupt communications and navigation systems, causing significant problems for modern technology. Whether you experience a geomagnetic disturbance as beautiful or problematic depends entirely on your point of view and your relationship to the systems being affected. The aurora reminds us that events in themselves are neutral, gaining meaning and value only through the lens of human interpretation. This relativity of perspective extends to the aurora's role in different cultures and historical periods. What medieval Europeans might have interpreted as an omen of divine displeasure, modern scientists understand as evidence of our planet's magnetic protection system functioning normally. Neither interpretation is inherently correct or incorrect. They simply reflect different ways of understanding and relating to the same phenomenon. The aurora also serves as a bridge between different ways of knowing. Indigenous knowledge holders who have observed the aurora for generations possess insights that complement and sometimes challenge scientific understanding. Their observations of correlations between auroral activity and weather patterns, animal behavior, or seasonal changes represent a different kind of empirical knowledge, one based on long-term observation and cultural memory rather than controlled experiments and mathematical models. This multiplicity of knowledge systems surrounding the aurora reminds us that truth is often richer and more complex than any single approach can capture. The aurora benefits from being understood both as a plasma physics phenomenon and as a spiritual presence, both as a manifestation of solar-terrestrial interactions and as a source of cultural meaning and personal transformation. The aurora also challenges our assumptions about permanence and change. While the basic physics that creates the aurora has remained constant throughout Earth's history, the specific characteristics of auroral displays are never exactly repeated. Each aurora is unique, shaped by the particular combination of solar wind conditions, magnetic field configurations, and atmospheric properties present at that moment. The aurora is simultaneously eternal and ephemeral, constant in its underlying nature but endlessly variable in its specific manifestations. This paradox of permanence and change reflects something fundamental about existence itself. Like the aurora, we are shaped by constant underlying principles yet expressed through endless variations. The aurora becomes a mirror in which we can see reflected the basic patterns of growth, change, and renewal that characterize all living systems. The aurora also exists in relationship with human creativity in ways that extend far beyond its role as a subject for photography and painting. The aurora has inspired musical compositions that attempt to capture its rhythmic pulsing and flowing movements. Writers have struggled to find words adequate to describe the experience of witnessing the lights, often resorting to metaphors drawn from dance, music, and dreams. The aurora challenges human creativity by presenting a phenomenon that seems to exceed the normal capacities of language and art to represent. This challenge to human expression is part of the aurora's gift to culture. By presenting us with beauty that strains the limits of our ability to describe or recreate, the aurora pushes artists and writers to expand their techniques and find new ways of conveying experience. The aurora has been a catalyst for innovation in artistic expression, inspiring new approaches to capturing motion, light, and the relationship between terrestrial and cosmic scales. The aurora also serves as a natural calendar that operates according to cosmic rather than human rhythms. For people living in polar regions, the return of the aurora after the bright summer months signals the beginning of winter's approach. The increasing frequency and intensity of auroral displays mark the progression of the dark season, creating a temporal framework that connects human experience to the larger cycles of solar activity and planetary motion. This cosmic calendar operates on multiple timescales simultaneously. The daily rhythm of auroral activity peaks around magnetic midnight. The seasonal variation brings more frequent displays during the months around the equinoxes. The 11-year solar cycle creates longer-term patterns of more and less active periods. These overlapping cycles create a complex temporal texture that connects observers to rhythms operating on scales from hours to decades. The aurora also teaches us about the relationship between local and global phenomena. While each auroral display is intensely local, visible only from certain locations and lasting for limited periods, it's also part of global systems that connect the polar regions to the sun and to each other. The aurora that appears over Alaska is connected to simultaneous displays over Siberia and Scandinavia, all part of the same global response to solar wind conditions. This connection between local and global scales reflects the aurora's role as a visible manifestation of planetary scale processes. When you watch the aurora, you're witnessing your planet's response to space weather, seeing evidence of global systems that normally remain invisible. The aurora makes the abstract concrete, transforming complex geophysical processes into immediate sensory experience. The aurora also demonstrates the importance of position and timing in human experience. To see the aurora, you must be in the right place at the right time, under the right conditions. This requirement for specific positioning makes each auroral encounter feel significant, earned rather than casual. The aurora doesn't appear for everyone everywhere, making it a privilege to witness rather than an entitlement. This selectivity of the aurora creates communities of observers who share the experience of having positioned themselves correctly to receive the aurora's gift. Aurora watchers develop a sense of kinship based on their shared commitment to seeking out the conditions necessary for observation. They understand the patience required, the discomfort endured, and the joy experienced when the lights finally appear. The aurora also exists in relationship with hope and patience in ways that mirror many important aspects of human experience. Aurora watching requires faith that the lights will appear, even when skies remain dark for hours. It demands persistence in the face of uncertainty, commitment despite the lack of guarantees. These qualities that the aurora cultivates in its observers serve them well in other areas of life where patience and faith are required. The relationship between effort and reward in aurora watching also reflects broader patterns in meaningful human experience. The aurora teaches us that some of life's most beautiful moments cannot be forced or purchased, but must be approached with the right attitude and preparation. The aurora rewards those who make themselves available to receive it, but it cannot be commanded or controlled. As we draw toward the close of our auroral journey together, we find ourselves enriched not just by knowledge of plasma physics and magnetic fields, but by a deeper appreciation of the relationships that connect us to the cosmos around us. The aurora has shown us that we live not on an isolated world, but as part of an interconnected system that extends from our planet's core to the edge of the solar system. The aurora has also reminded us that wonder and understanding can coexist, that scientific knowledge enhances rather than diminishes our capacity for awe. In learning about the aurora, we've discovered that the universe is both more complex and more beautiful than we might have imagined, full of phenomena that challenge our understanding while inspiring our imagination. Tonight, as the aurora continues its ancient dance across the polar skies, it carries with it all the stories we've explored together, the science and the folklore, the physics and the poetry, the local and the cosmic. In its shimmering curtains of light, we see reflected our own journey of discovery, our endless quest to understand our place in the universe, and our profound connection to the forces that shape our world. The Northern Lights remind us that we are part of something larger than ourselves, participants in cosmic processes that began long before we existed and will continue long after we're gone. Yet our capacity to witness and appreciate the aurora makes us more than passive observers. We become conscious participants in the universe's ongoing conversation with itself, aware beings capable of finding meaning and beauty in the dance of matter and energy that surrounds us. As the aurora fades with the approaching dawn, it leaves us not with endings but with beginnings, not with answers but with deeper questions about the nature of existence and our place within it. The aurora is both a phenomenon to be studied and a mystery to be contemplated, both a source of scientific knowledge and a gateway to wonder that connects us to the infinite creativity of the cosmos itself.